Hello everyone, welcome back. Today we'll start with episode 4, exploring analytical data processing. Analytical data processing typically uses read-only or read-mostly systems that store vast volumes of historical data or business metrics. Analytics can be based on a snapshot of the data at a given point in time or a series of snapshots. Basically, uh, analytical data processing is just analyzing historical data where we read the data most of the time only without changing anything of its content. We'll extract, for example, historical type of data. For example, a 1 week old type of data where we won't have to edit anything as it's already historical, and we'll do analytical data processing on it. The specific details for an analytical processing system can vary between solutions, but a common architecture for enterprise scale analytics looks like this. Okay, so basically we have a database and a file storage system that's stored in tables or in folders, and I guess this would be we can read about we can more read more about it. Operational data is extracted, transformed, and loaded ETL into a data lake for analysis. So basically, we will extract the data and prepare it into a data lake for analysis. Data is loaded into a schema of tables, typically in a Spark-based data lakehouse, with tabular abstractions over files in the data lake, or a data warehouse with fully relational SQL engine. So we have two options here. When the data is loaded, when the database and the files are loaded, they're loaded into two possibilities. Spark-based data lakehouse with tabular transactions, or a data warehouse with fully SQL with a fully relational SQL engine. It's either tables or it's a data warehouse with tabular transactions. Number three, data in the warehouse may be aggregated and loaded into an online analytical processing OLAP or cube. Aggregated numeric values measures from fact tables are calculated for intersections of dimensions from dimension table. For example, sales revenue might be totaled by date, customer, and product. So basically, we'll load the data into an online analytical processing model or a cube, where we'll have measures or we'll have measures the data will make up the measures of the cube or the OLAP model, online analytical processing model. The data in the data lake, data warehouse, and analytical model can be queried to produce report visualizations and dashboards. So basically, after they're in the warehouse and they're ready to be processed, we can extract them to produce reports, visualizations, and dashboards where we'll see where we'll understand more about our data. For example, the percentage of a certain product selling over other products, how often a certain product is selling, how much is the revenue from our products, for certain, for example, the percentage of each product, how much does it contribute to the final revenue? That would be several examples of how we would work on how we would visualize the data and report it, where it would produce reports or visualize it and make dashboards of it. Data lakes are common in large-scale data analytical processing scenarios where a large volume of file-based data must be collected and analyzed. Now, when we have large amounts of data, we'll need to place them in data lakes. Where a large When we're talking file-based data, we'll use data lakes. Data warehouses are an established way to store data in a relational schema. So basically, when we say data warehouse, we're talking about relational tables, as in structured data. But if we're dealing with files, then we'll say we're using data lakes. Data warehouses are an established way to store data in a relational schema that is optimized for read operations. Okay, so it's meant to be only read without any writing involved, without a lot of writing involved. Primarily queries to support reporting and data visualization. Data lakehouses are a more recent innovation that combine the flexible and scalable storage of a data lake with the relational querying semantics of data warehouse. Now, lakehouses, this is lakes and this is warehouses, but there is something called data lakehouses. Now, lakehouses are a more recent innovation. Now, it's a new idea. Now, from the name, I can guess that we're combining both ways, lakes and warehouses. The flexible and scalable storage of data lake, where the data lake is commonly used for its scalability and flexibility of its storage, with the relational querying semantics. Now, warehouses are optimized for querying semantics. So basically, lake houses are a new innovation that can be used. The table schema may require some denormalization of data in an OLTP data source, introducing some duplication to make queries perform faster. So basically, we'll need to drop the denormalization. We mentioned previously that our relational models are all normalized, our relational tables are all normalized, but sometimes we need to have some sort of duplication to make the processing faster, where we should denormalize our models. An OLAP model, OLAP model, is an aggregated type of data storage that is optimized for analytical workloads. As we mentioned previously, the model is the OLAP model, which is the online analytical processing model, is optimized for analytical workloads where we analyze our data and process it properly. Data aggregations are across dimensions at different levels, enabling you to dial up and down to view aggregations at multiple hierarchical levels. Now, when we're dealing with a lot of data, we'll have to aggregate some data together. We'll need to, for example, combine two different columns to each other to make reading the data easier. But sometimes we have multiple aggregation levels, so it will enable us to look at the hierarchical level. Some multiple aggregations can be made, and it can be on multiple levels. For example, to find total sales by region, by city, or for an individual address, because OLAP data is pre-aggregated. Queries to return the summaries it contains can be run quickly. Now, if I'm trying to find maybe the region, city, and an individual address can be all aggregated. For example, first I look for the region, and if I want the city or I want the individual address, it would be all data aggregated to each other to be used together. Where I'll need to remove the aggregation to process the data, or I could just rely on the aggregation to get the data that is, for example, in a specific region, Data in a specific region would be aggregated together, data in a specific city would be aggregated together, and so on and so forth. Different types of user might perform data analytical work at different stages of the overall architecture. For example, data scientists. Okay. Now, analytical people in our jobs will have different types of working with data. We will work with data differently. Now, it happens at different stages of the overall architecture. Let's read about them. Data scientists might work directly with data files in a data lake to explore and model data. Now, data scientists would access the data files directly to explore and model data, to explore and make AI models or machine learning models out of them. Data analysts might query tables directly in the data warehouse to produce complex reports and visualization. Now, in the warehouse, where data analysts would use data in the data warehouse to make reports and visualizations to understand more about the data to understand more about what our business and how our business is working. Business users might consume pre-aggregated data in an analytical model in the form of reports or dashboards. Business users, so pre-aggregated data, let's say it's aggregated per region, per gender, per city, per age group, whatever. So they would use it for an analytical model to make a report about certain type of group or a certain group of people. So that would be the business users. Basically, we finished about exploring analytical data processing. Thanks for watching.